Hi everybody, I wanted to walk you through how the drop stuff lab from Monday should have gone. Kind of highlight some points. First thing you did was test dropping a heavy object and a light object from the same height at the same time to see which one would land first, if any. Looking at your results that you submitted, most people saw that it didn't really matter whether you had a heavy object or a light object. Assuming air resistance isn't really a factor, mass doesn't affect how much something, the rate at which something falls. On Earth, everything falls at the same rate as long as there's no air resistance. So, same free fall acceleration. The next thing you did was test a round object versus a piece of paper, and hopefully you saw there that the round object free fall acceleration was greater. So it landed first. And that has to do with this paper having a lot of surface area and not a lot of mass to it. So this surface area catches the wind kind of like a parachute. And so that slows the paper down, and so it doesn't fall like a normal object does. Last thing you're trying to figure out is, what is this acceleration? If everything on Earth is supposed to fall at the same rate, what is that rate? So I've drawn a little picture of a person standing on a chair, dropping an object 2.5 meters, and let's say that they timed it, and it was 0.71 seconds to land. And I asked you to use your delta x equals vi times t plus 1/2 at squared equation to find a. A is what we're looking for. So we've got the time. The initial velocity, since you're just dropping the object, you're not throwing it down or throwing it upward, that initial velocity is 0. So vi is going to be plugged in as a 0. Finally, your delta x, that's displacement. That's the difference between where the object starts and where it stops. So our object fell 2.5 meters down. Now, what I would ideally want you to use is, if something falls down, its displacement is negative. It's 2.5 meters below where it was let go from. So I'd have negative 2.5 for the displacement, 0 for vi multiplied by 0.71 plus 1/2 a 0.71 squared. So now we simplify things. Negative 2.5, 0.71 times 0 is 0. So you got 1/2 times a. 0.71 squared is 0.5041. Move on to the next line of work. Do the 1/2 times the 0.5041. You get 0.252 times a. Divide negative 2.5 divided by 0.252, and you get negative 9.9. And our units for acceleration are meters per second squared. Now, if you did this and I saw a lot of results were all positive, that just means that you used a positive displacement. That's not the end of the world, that's totally fine. From this point forward, we're going to use displacement when things fall down as a negative value. But if you got a positive value of close to 10, that's fine. So we're just going to round this answer to approximately 10 meters per second squared. That is the free fall acceleration on Earth for all objects, assuming there's no significant air resistance to deal with. What does that mean? Well, that means that when something falls, every second that it's falling, it's going 10 meters per second faster. So if this is a picture of a hand, excuse me, holding a ball, 1 second later that ball might only be, well, let's go a lot closer. At 1 second, the ball is here. At this point, it's falling downward at 10 meters per second. 1 second later, so we draw this interval bigger, it's now falling at 20 meters per second. You kind of get the pattern here, but 1 second after that, it's now falling at 30 meters per second, and so on and so forth. Does that continue forever? No, there is something called terminal velocity. We'll get into that when we get into forces in our next unit. But there is a point at which it stops speeding up because there's eventually enough air resistance to keep it from going faster. Think a person jumping out of an airplane doing skydiving. They don't just speed up forever. Eventually there's going to be enough wind pushing up on their body that they stop speeding up. But they're going really, really fast. Same thing if you dropped a penny off the top of the Willis Tower or Sears Tower. It's not going 300 meters per second by the time it lands. It's not going to kill somebody falling off the Sears Tower. Instead, that penny hits terminal velocity going really fast, so it would hurt if it landed on your head, but it's not going to like impale your body or crush your skull or anything. So this negative 10 meters per second squared, super important value. We're going to just use that as our acceleration moving forward.